Hi, everyone. Thank you so much for joining us today. This is our third episode of the Graph Gurus webinar series for developers. And today we have a presentation titled Detecting Fraud and Money Laundering in Real Time. This is actually going to be our first, or actually a part one, because we have so much to talk about. We're going to do two parts. This presentation will cover more of the phone scam fraud, and then for our episode 4, we're going to go more into the anti-money laundering focus. So my name is Emily McAuliffe, and I am just going to go over some housekeeping items for the webinar today. Everyone on the webinar is muted except for obviously the hosts, and so if you need to chat with us, you can use the Q&A, actually the chat feature, and then you can also use the Q&A feature for questions. We'll take the questions at the end of the webinar, but you can actually ask at any time when you have a question, and then we'll just go back to the question at the end. So the webinar is going to be recorded. It's being recorded, and we'll send you the link with the presentation and the steps, the reproducible steps that we're going to be showing today. You can go to our website right now and download our developer edition if you haven't done that already. So I'm going to go ahead and start introducing our speakers today. And Victor Lee is our Director of Product Management. And as you can see, has a great background with a focus in graph data mining. So Victor, I'm going to hand it off to you to take over here.
Thank you, Emily. It's great to be here again with our audience, our set of, we call them, graph users. We can call you graphistas, and we're going to try to turn you into graph gurus of your own. I'm happy to be joined today by Dr. Dan Hu, who is one of our graph gurus. He is an actual quantum physicist. First studying physics in China and then at UC Merced. He's been with TigerGraph for 3 years, and he is uniquely qualified to present today's talk on anti-fraud because he developed the entire solution almost single-handedly, working with one of our customers to understand the problem, to see how it could be first looking at a machine learning architecture, and then applying G-SQL to that and enhancing the capabilities of G-SQL alongside that. So I'm going to be really excited to hear how Dan is going to talk about his work. I'm going to give you an overview of the task for about 5 minutes, and then I'm going to turn it over to Dan. So as we said today, we're talking about using graph to assist with fraud detection. And the particular example case we're going to look at is a real use case, fraud in phone communication. And this is a massive worldwide problem. And when I'm talking about fraud, I'm talking about not only things that you normally think of fraud as, something financial, but it also includes just things that are unwanted sales calls or even, crank calls. But I bet most of you out there have received some number of robocalls. 18 billion robocalls received in the US in 2017. But this happens in every country. So we're talking about spam, we're talking about scams. The people doing this are very agile. They can spoof phone numbers so they look like their local numbers. They move quickly from one number to another. So it's hard to track them down. And that's why you have to apply the best technology to keep this, to try to capture this and to try to, customers don't want to see this. So the telecom providers are seeing what can they do to increase customer satisfaction, to cut down on just unwanted phone calls or ones that are actually, again, leading to actual financial crimes. So the customer we worked with is China Mobile, and because they are in China, the world's most populous country, they are the world's largest telecom. When we started working with them, they had around 450 million subscribers. It's now at 600 million. They process more than 300 million calls a day at a peak rate of over 10,000 calls per second. And so they needed something that could, in real time, that is, while a call is going through and has not even been answered yet, to detect if this call is likely to be of some of that unwanted activity. So we're going to look at how we went about doing this in the next slide. So our solution was to provide real-time, graph-based machine learning and decision to detect different types of unwanted or fraudulent activity. So first, we constructed a graph database to record all the phone calls received in a 2-month sliding window. So that comes out to, at the time, it was some 600 million phone numbers, and that's including both of their customers and people that they call or who call their customers. So it includes both in-network and out-network phone numbers. And then the phone calls between those phone numbers. So that comes to about 15 billion phone calls over a 2-month period, recording who the caller is, that phone number, the phone number being called, what time the call starts, and how long the call lasts. And that comprises the call record. And then we need real-time graph updates because, as we mentioned, again, there are more than 10,000 calls coming in per second, and we need to capture all those calls because those calls, as we will show later, the past calls are indicative of determining whether the current call is likely to be fraudulent or not. So you have to capture all that activity, and you have to capture it in real time because, as we said, this activity, the people who are doing this unwanted activity, they move very quickly. If it's a robocaller, they're calling maybe 100 calls per second. So you have to capture this data right away. As we'll get into in the machine learning, we're extracting 118 graph features per call in real time. We periodically use these features to retrain the machine learning model using a selected set of a couple million calls from the 15 billion. And then once we have the machine learning model, it is applied in real time. As we said, those 118 features will be extracted in real time, applied to the model to see whether a call appears to be unwanted or not. And we did this work in 2016. It was deployed at the end of 2016, so it's been running for almost 2 years now. And if you can go to the next slide, here we show just a sample of some of those 118 graph features. So what these are small little graph patterns from a starting number, the person who is making the call. So if you see in the figure on the left, phone one is the person who is making a call. And we show here 5 different features. I'll just talk about one of them so you understand, and then Dan will talk about them in more detail later. Around the middle of the figure, you see something called many in-group connections. And what this is we start from the caller, and we see who they have called recently. So these are their neighbors, call neighbors. And then we see, have they called one another? So do the people that phone one has called, do they form a community? If they do, that means they know each other in some way. They conduct, whether they're friends or business associates, it means they have some reason why they call each other. that's a sign of legitimacy. So that increases the likelihood that phone 1 is a legitimate caller. But not necessarily, because maybe phone 1 obtained a phone list. And so he's been calling all these people. They know each other, but they don't know him. So whether this matters or not, we leave it to the machine learning. So the purpose here is to extract the feature. These are features of interest, and we let the machine learning tell us whether this is indicative of a good phone call or a bad phone call. And if we go on to the next slide, this is a high-level view of how our system is used, and Dan will go into more detail later. But I will start out by saying, on the left, you see a phone call. A phone call is being made, a real-time call event. And we know who the caller is, who they're calling, and what time. So the call isn't even finished. It's just starting. And it hasn't even been answered yet. So that information goes into our graph. And again, we extract the 118 features, and we apply so for each feature, you get, some score or some small output from each one. And those go into a combining model, which takes a look at all the features and comes up with an overall assessment. Is this likely to be fraud or not? And if it is, what type of fraud? So each phone number in the graph has with it a fraud flag. The fraud flag, if we recently determined that this caller is making bad calls, then we set the flag. And so that's why if another call comes in soon afterwards, we don't have to re-examine. We've already determined that this is a bad caller, and so we can immediately just tag the new call as also fraudulent. But those flags will expire after a certain amount of time. And so again, in real time, we are collecting the features, we're computing a composite score, determining whether that is considered fraud or not. So we either set or clear the flag. And if it is fraud, we also can judge what type. Our model has, actually it's a combination of models to determine a couple different types of fraud. And lastly, I'll just go back and refer to the bottom part of the figure where it says call detail records. So now the call is completed. So when the call first started, we made the assessment. And with the assessment, we actually, China Mobile is actually displaying a message on the person's mobile phone. If it's fraud, it actually displays a message saying, hey, this seems to be fraud. It seems to be this type of problem. So you may not want to answer this call. Once the call is completed, then we have the complete CDR, call detail record, and that information is added to the graph because if you remember, the graph features look at the past call activity. So we need to record all this call activity so that the future calls have this information available to make their assessments. With that, I am now going to let Dan give you even more detail. So Dan,
yeah,
welcome, and let you go.
Okay. Hi, hello everyone. Let's take a look at how the TigerGraph do the machine learning to build this fraud detection system. So before we go to the details, let's first look at the raw data. What kind of data do we have? As Victor mentioned, we have the CDR data, which is the call history of all phones. But actually, it can be represented as a graph with phones as the vertices and the edges, the phone-to-phone edge representing the phone call relationship among phones. So here we didn't build the edge to record all the call events because look at our data for China Mobile, they have 300 million daily updates every day. So it's not possible to record all those call events on our graph. And also for our fraud detection purpose, it's not that useful because unless you want to look at very detailed of each call, you need those events. But for detecting whether it's a fraudulent events there, we just look at some statistical data. So instead, what we did is we built an aggregate edge. So on this edge, we record the number of calls between those two phones and also record the total durations of those phones. And we have a list to record the recent days that those two callers are contacting each other. And also we record the number of rejections. So in this way, we can limit our edge numbers. And as we mentioned, on each vertex, we actually added a flag to indicate the fraud type of this phone. And also we have an expiration time for this flag. And this expiration time actually depends on the fraud type. Because we found that once a phone is tagged as a scam or a good phone number, then it's more stable. It will we will give longer expiration time than the phones target as advertisement or harassment, because those type of phones, they might, as we aggregate the information, they might turn to the scam phones or go back to the good phone. So we give shorter period of expiration time. So that's basically all the raw data we have, all the information we have to do the fraud detection. So all our features are actually built from those raw informations. Let's now look at the workflow of our query. How do we do the fraud detection based on those informations? So as Victor just mentioned, our workflow for the fraud detection query is like this. So when the call event comes, we extract the caller IDs. So the first scenario is we have given this phone a fraud type recently, so it's not expired yet. So that in our query, we can reuse its attributes, the fraud flag, and return the fraud type immediately. In this way, we can detect the fraud phone in real time, so that even before the callee answer the phones, they already know that the fraud type. This is a very simple case. And look at the second scenario. That is when we don't have its fraud flag yet, or when its fraud flag is expired. So what we need to do is our query will do the feature collections for this phone, for the caller or callee if one of them is expired. We collect their features, then we send this feature vector into a previous trained model classifiers, and we do the scoring and do it in the real time. After we got the score, we got the fraud type, we update the fraud attribute, fraud flag attribute, and at the same time returns the fraud types. And TigerGraph can do this in real time. Normally, the query response time is like 20 millisecond to 50 millisecond. TigerGraph can do this. One of the reasons we can do this in real time, because for this type of point query, we actually only need to traverse a subgraph, like for this caller or for this callee, we only traverse a subgraph. So the subgraph compared with this entire database is very small. We can do a subgraph traversal and get the features out, and then we do scoring. So that's why we do it very fast. And at the end, the callee still can get the call type, the fraud type, before answering the phone. So let's talk about more on the how TigerGraph do the machine learning. So first question people always ask, why use TigerGraph to do machine learning? So as we mentioned, first, it's fast. we do real-time response for both feature collection and scoring. Second, it's efficient because TigerGraph, our query actually support aggregation. When you do the graph traversal, we actually provide you ways to do aggregation, to aggregate information. So that means that we can collect multiple features in just one traversal. And it's also easy. We can build very complex features. Those features in the relation database, it might require multiple joins, but in our here, it's just multiple hop traversal, and we can get the feature in a really fast way. So when we do the machine learning, for China Mobile, we collected 118 graph features because of our query. And we performed the fraud scoring with multiple machine learning models in the real time. So we have implemented the logistic regression and to do the classification of the fraud type. And also we use the K-clusterings to do the clusterings for the scam funds or the fraud funds. Actually, TigerGraph, you can do any kind of machine learning models as long as you know how to do the scoring. So machine learning models are trained offline, but its parameters are stored as configuration files for the G-circle to use for the real-time scoring. So, and also, how do we train the data? Train data the same as before, like we got the data labels. Initially, we got some data labels from the police reports and from some online third-party sources. We got phone labels. Then we collect features for those training samples. We get some candidates, and we get a feedback from the China Mobile so that we can further to improve the accuracy of our model. After several rounds, our model got very good performance. And the training, and also our G-circle also provide the capability that we can collect the training data features in batch and store it into a CSV file so that for the future trainings, it's the same as the normal model training. So now let's look at how do the TigerGraph collect features. As Victor showed this figure before, there's a lot of good features you can collect from graph. For example, for a good phone, a customer with a good phone, when they call the other customers, majority of the call will be returned, will have a callback. This shows that the familiarity among its target and itself, and also shows it's a good phone. And also other features like stable groups. When a good phone calls, they usually call a stable group of people regularly, and those people always call back. But for the bad phones, they usually don't happen. They just pick up the target pretty randomly, and they won't have this long-term relationship. Yeah, like the long-term relationship. Long-term relationship is looking at whether this phone has called them regularly every month or every weeks. We can use this to distinguish good phone with bad phone. Now, other things like Victor mentioned, the in-group connections. So good phones always call their friends, and the friends might know each other. They have very good in-group connection. Even they don't have in-group connection, we also can look at whether do they have a common friend, whether they call the common third person. All those features are not shown, or very less are shown on a bad phone. So let's look at the more detailed definitions of the two features, the stable group and the in-group connection. So stable group, we define stable group by try to look at the phones in the target group, whether this phone has a regular calls with a source phone. So the stable in-group connection, we look at phones in the target group, whether they have regular calls among themselves. So for the stable connections in China Mobile project, we define it in the following way. So a stable connection, they must have both call and call back between those two phones. And also for each edge, they need to have like number of calls must be larger than a given limit. The total duration of the call must be larger than a given limit. That's a definition of the stable connection. So let's look at how we collect those features on the graph. So the idea is simple. We just start from the source, the given phone, do a one-step neighbor traversal. We can find out stable group. How do we do that? We just find out target. If it has both outgoing edge and incoming edge connected with your source, then you are stable. You are stable target. So in the graph database, how do we check whether the target is stable connected? Because we have a definition like here, not only both directional edge, but also they fulfill some requirement. So what we can do is, one thing we can do in the graph database is, if the source can send a message to the target, we can do this thing. When we traverse the phone edge, we check whether it fulfills stable connection relationship, check those two requirements, the number of call and total duration. If it fulfills, the source can send a count to the target. Then we look at the incoming edge, that is phone reverse edge. We have a phone reverse edge to show if target called source, but it still starts from source. So we check it. If the phone reverse edge also fulfills those two conditions, then we send another count. Then we just look at the count received on each target. If them have a count of 2, that means that this target has a strong, has a stable connection with the source. In this way, we just find out or count how many targets has a count 2. Then we can easily find out the stable group for this source. So then look at the in-group, the stable in-group connections. So stable in-group connections is similar to the stable group of the source, but it requires one more step traversal. So the idea is step 1, we still start from the source vertex. We do a one-step neighbor traversal. Then we need to mark our targets, because those are the targets inside the target groups. And our second step is actually we want to limit our traversals among the target groups, because we are looking at in-group connection. So we need to give a label for each vertex so that indicate it's in the target group. Then we, starting from each vertex in the target group, we find out there's one-step neighbors and check whether it has a stable neighbors connecting with them. So just check the stable target for each vertex to check how many neighbors has stable connection. In here, in order to check whether it's a stable connection, it's a little bit different than the previous one. Previous one, you only have a source. You can send a count to the neighbors. You can find out the count equal to is stable. But here we have multiple targets. Each targets are doing the same thing at the same time. So instead of sending counts, we can use a map. We can use a map to record its neighbors. And also, if we traverse the phone edge, we store the phone edge information into this map with the target ID as a key. If it traverses phone reverse edge, we store the phone reverse edge information into this map and record with the same ID. Then at the end, we just look at each target, look at its map, whether for each neighbor in this map, whether it has 2 type connections that fulfill those 2 conditions. If it is, then we have a stable in-group connections with another target. In this way, we can figure out whether this target has an in-group connection, and we can count how many strong, stable in-group connections is here for those target groups. So that's the ideas how to collect the stable in-group connections and the stable groups for a given source. So let's take a look at a demo to look at what's the G-circle query, how do we implement those 2 features just in one query with 2 step traversals. So here is actually our Graph Studio API. In here, actually you can do the graph, design the graph schema, do the data loading, and then write queries. And the query here, I use this because it has a syntax highlight, so I can easily show the query. So let's first look at the schema. The schema here is quite easy. we only have a type vertex called phone, and it has an edge called phone edge, phone to phone edge connecting to the phones. Actually, we have another edge called the phone reverse edge. It's just reverse edge. It's not shown here. So let's go back to our query. So our query is called the feature collections. So the input is quite easy. We give the source phone ID, like which phone you want to check, and we also give the conditions for the stable connection. We have remember we have two limits, the duration limit and the number call limit. So look at the queries here. So we have two blocks, like line 18 to line 35 is one block. Another block is 38 to like 63. So those two blocks is, as we mentioned, first we need to traverse from our source vertex to one step neighbor traversal, and then we need to go from the target groups and one step traversal to its targets. So the G-circle query is similar like circle query. It has a select statement, but the difference is our from is not from a table, but instead we from an edge. We from a vertex site, like this one, the line 19. We have a seed vertex site, and we specify what edge, what type of edges you want to traversal, and we specify the target phone type. Here is phone. So this is the from select statement. In here, we actually have two blocks. One is called accum, another is called postcum. As I mentioned previously, we actually provide aggregation capabilities while you do the graph traversals. This is actually achieved by using accumulators. We have a lot of type accumulator. Like line 3, we define a sum accum, as we want to collect the stable count. We mentioned that we want to count whether it has two connections with the source. So we have a sum accum. And we also have a group by accum. This can be used like a map. So you can store your neighbor information. Your key is your neighbor ID. Your value is the list, because if you have two edges, then you have the list have size 2. So these are accumulators. We call it local accumulators, because those actually build on each vertex. So go back to the accum block. The accum block, you can assume that you're at the edges. You have the information of your source attribute, your edge attributes, and also your target attributes. But in here, the main target is to give a rule to how to update your target accumulators. So for here, for this block, we only want to update the stable count. If it fulfills some condition, it updates the count. But as we know, it's on the edge. So if you have millions of edges at the same time, those things are executed in parallel. So in the accum clock, we cannot know what's the final result for stable count. So that's why we go to post-accum. Post-accum is like a reduce. If you think like accum is like a map process, the post-accum is in a reduce. It's actually on the vertex. Those accum is on the edge, post-accum is on the vertex. Here we are on the target vertex. So we just check how many counts it received, because right now in the post-accum, those counts are already updated by all those edges, outgoing edges. And if this count is equal to, as we talked about, that means that it has a stable connection with your source target. So we can mark a label. This label, this is also a accumulator called the all accumulator. So it's just a flag to indicate whether it's in the stable group or not. So we can label it as true, or you can even count how many stable target you have. So, and also in the first block, it's actually, so that's our accum and the post accum. Basically is gives you a way to do the graph traversal by one step edge and collect information on the vertices, and then you have a halving block so that you can limit your target site. So let's go back to our algorithms. As we mentioned, we have two blocks, two select blocks. One block is actually used as collecting the stable targets for the source. So we look at this block first. So in here, as we discussed, we use the stable count to identify whether the target is stable or not. It fulfills condition, it adds a count. But at the same time, we also label whether this target is in our target group, because our target group is defined as if the source called you, you will be in the target group. So that's why we have edge equals to feng type, then we target you as in the target group. We need this information, that's for the second block traversal. But for the first block, we only need to update the count. In the post-queue, this is on the edge. Once after the queue, each target vertex will receive the message and add their count automatically. Then in the post-queue on the target vertex, we can check whether this count is ready to, is in your stable target group. And also at the end, we are not looking at all the targets, because in here at line 19, you mentioned that you want to traverse both edge, feng edge and feng reverse edge, but the target group is only defined for the feng edge. So we have a halving block so that all the targets in this target group site, only including targets, has been marked as in the target group site. In this way, at the end of the first block traversal, we already have a set of vertices that only in for the target groups. Now we move to the second block. The second block is actually for the in-group connections. So you can see here, the edge is almost the same. We traverse both feng and feng reverse edge because we want to know whether the stable connection. We need both outgoing and incoming edges. So that's why we use both feng and feng reverse. But on line 14, we add one more condition. We want to limit our target as in-group targets, in target groups, so that those edge traversal happens only for the edges inside the target groups. So this is how we got in-group connection. And for here, we want to know whether our target group has a stable connection within the target groups. So in the queue, we don't do any filters. You can actually do filters, but we don't do any filter. We use a so-called the group by accumulator. Basically, is a map. It's a map key with the target ID, value with the edge values. So for here, we just collect this information for our target, every vertex in the target group. So we update the source accumulators. So the update is like this: you give the target ID and you provide your own. The call info is a tuple. You define it at the beginning. You want to collect the total duration and you want to collect the number of calls. That's the condition for the stable connection. And we also added the edge there because we want to show it in the visualization. You can see the edge. So we put the edge here. Actually, for the real feature collection, we don't need this edge. We just need to collect necessary information. Anyway, this line 43 actually gives you the rule how to update your source target neighbor info. Then in the post queue, in the reduce on the vertex, on the source vertex, you just go through your neighbor site to see which one is stable. If the both fulfill the condition, we still use a stable count to find out that they are in a stable. If the stable count equal to 2, we can safely add it into a stable neighbors for our target in the target groups. So in here, we didn't do the filtering before because in the real case, you might want to know the information of the both edges, and then you do your definition of your stable connections. But here we just local, we need one edge we can do find it's stable or not. But in the real case, you might think like maybe the number of calls add together bigger than some value, or durations add together bigger than some values. So that you have all those edge info at the same vertex, then you can do this judgment. But anyway, in this way, you find out your neighbors, whether it's in your in-group neighbors, whether it's in the stable connection with you. For here, we also added those edge into our in-group stable connection list. And then we print it out. Once we have a print statement, actually, they will convert those data structures into a JSON format and returned. So that's our queries. We have just 2 travels, and we reuse the first results. So that's why I'm talking about like you collect the stable target group and the stable in-group connection in one query. They can, if they are sharing the traversal, you can reuse those informations. You don't need to do a retraversal, so that it's very efficient. In this way, actually, we build a query to collect 118 features for the China Mobile to do the feature collection, and we can return this as a feature vector so that we can feed it into a scoring subqueries to scoring for this phone number. So now let's look at how are we going to look at when we run it, how do we get the results? Run query. So I have a fake data site loaded. So let me see, it wants to know the 2 parameters, the number of calls. We gave 6 number of calls, like duration like 60 or 60 minutes, 60 seconds. And the input phone ID, I gave 1. Then I can run the query. Once you run the query, you can see in the bottom part, it shows the returned results, those print statement as a graph in the Graph Studio. So let's look at it. So basically, 1 is a source phone, and you can look at it here. We actually find in-group stable connection groups like phones 8, 9, and 10. They both has phone call strong connections with each other, like they have number call 7 and total duration is 140. And other phones, they might have, look at here. If I click it, it actually do a 1-step traversal. It shows that phone 7 and phone 1, they have stable connection. They have both direction calls, and the total number and total durations are larger than the given values. So yes, this shows that this query actually gives the correct results. You can see. Okay, so I think this would be everything I want to talk about today. Let's go back to our slides. So all the information about this query and the schema you can find out on this web page. You can download it. It's a ecosystem, so it's a public accessible. You can through this link, you can find out the codes. So Emily.
Okay. Yeah. Victor, I don't know if there was a question that was sent via chat and not via the Q&A. If anyone has questions right now, please feel free to send their questions in now. So I don't know if you, Victor, had a chance to look at that question yet.
Yeah, we're going to, if you do have a question, send it in. We're going to stay online for several more minutes. I'll just repeat the questions that came in through the chat line so that everyone hear them and so that they will show up on the recording. The first question was, how do you process multiple calls at the same time and make sure that the bad phone detection is completed before the calls are made? I can answer that one. I don't know if Dan, you'd like to address TigerGraph, just the general capability of our engine. How do we process multiple calls and why are we so fast?
Okay, so let's go back to this one. No, this one. So actually, so our engine is it accepts multiple queries. So in order to make sure that the updates and the queries won't mix each other, we actually use the snapshot. So when query comes in, it has a snapshot of the graph it can see. So this query only works on this snapshot. So that's why the update from the real-time update won't interference with the queries. Which
So let me just, thanks, Dan. Just want to summarize that TigerGraph is a transaction-capable database. So that the ability to handle multiple transactions at the same time. You might not see that in all graph databases, but it's certainly supported in TigerGraph. So we are a transactional database. We are also a massively parallel processing database, MPP, which means we have the capability to not just handle a few, but handle many, many operations at the same time, whether that means that one query is trying to do a lot of work or multiple queries are happening at the same time. So that gives us the raw speed to handle individual events quickly and to handle, and then as Dan alluded to, we have concurrency control and transactional control so we can handle multiple operations. I will say a little bit about the hardware. I mentioned earlier that we handle at peak at least 10,000 calls per second. In order to achieve that, what China Mobile found, what they wanted to do was have replica machines. So we actually, their initial configuration was 5 machines. Each one stores the entire graph. And so they could each machine can also handle several calls, a few thousand calls. And by having 5 machines, then they were able to increase the few thousand up to 10,000. Now, this is not considered a distributed graph. This is considered a replicated graph. TigerGraph can support both replication and distributed. So I mentioned that they initially started with, I don't think I told you, we initially had fewer than 10 billion calls, and they're now holding more than 15 billion. That's still within one machine, but if they ever feel like they need to spread the data across multiple machines, they could do that. So they could go from, say, 2 machines to hold 1 copy of the data, and 5 or 6 replicas of that 2 machine configuration. So we support both scale out and HA replication. So that was.
If you want to look at the Q&A, Victor, there's a question about machine learning.
Right. Okay. So I will just read the question. To update the parameters in the machine learning model with the new incoming data, is the machine learning model completely retrained, or is it updated with the online learning technique? Thank you.
No online learning techniques. It just reads the configuration files. So we can support when you want to switch models, you have new parameters. The query can take a parameter to control whether we reload this configuration file or not.
Right. So I think also to add a little to that, to clarify the answer, it is a complete retraining when we choose to do it, or it's really when China Mobile choose to do it. I know there is such things as incremental learning. I think that's what the person is suggesting, and that's not what we're doing in this case. In this case, it's a complete retraining.
Yeah.
And I think there was one more question that came in through the chat line, so I'll just repeat that. Mm-hmm. Is each select block considered one G-SQL query, or is the code in this file considered one G-SQL query containing multiple select blocks?
it's each select. Actually, you can look at here. This is our entire query. This query, the select clause is actually a part of the query. This query has two selects, so they will run at the same time.
Right. And what you're showing here, Dan, for the purposes of this demonstration, you're showing just a small part of the 118.
Yes.
I know there was another module you had called the scoring. So I think there's one very long query for the 118. Is that correct?
Yeah, this is just a feature collection queries. So I only deal with the feature collection, and in here I only shows like 2 features. In practice, in our query for the China Mobile, we have, I think we use the up to 5 selects clause to do the traversal. Each block actually do a multiple feature collections.
Right, and so 5 select blocks would be 5 hops.
Yes.
Right, so yeah, unfortunately we're not able to share with you the entire code set due to proprietary concerns from our customer, but we are sharing everything that we discussed today.
Okay, there's another question in the Q&A.
How do you debug a complex GSQL query to see what's going on, such as in the accum or post-accum blocks? Want to maybe share some of your debugging tips, Dan?
Yeah, we have a log, so it's called log true. Like you can put any parameters here. You can target is in target group. You can put anything here, multiple variables here. Then it will show print log when you run a query in the log. So you can do the debug. And another thing is that's the most popular one. Like we might do the debug for the jQuery. I sometimes also I will print out, like do the print statement after a select statement. I print the vertex size to see whether it's fulfilled, and also I can look at the print statement. I can look at the any attributes in this target group. I can look at it what accumulators. For example, I can look at its target is in target group, so that I can print out all the vertices in this target group, only focus on these attributes. So basically, it's a log and the print statement we can use to do the debugging. Yeah.
Let's see. There were some other questions, I think, in the chat. So we're just going through those.
I believe we answered them.
Okay.
There are 3 there, and
Okay.
I believe we actually spoke all of them out. One showed up both in the QA and chat.
Okay,
so
great.
Last call, folks. And remember, we will be back in a couple weeks to continue our discussion with more emphasis on anti-money laundering.
Okay, great. I don't know if we have another slide that shows the link to the next webinar. Yeah,
Okay.
There it is. So our next one is on September 26th at the same time. So you can go ahead and register for that. And in this episode, we will be talking more about anti-money laundering. Victor, do you have any more to add to that?
No, I think we'll have a different guest speaker. It will sort of continue the theme of anti-fraud detection, but for those of you maybe in the banking industry know there are some special requirements, government requirements with anti-money laundering. So we'll kind of cover that as well. Different data set, different external requirements, but from a data side, it's fairly similar, but it's a great real world example.
Yeah, thank you, Victor. And this is Gaurav. I just want to add to what Victor said. it's a $1 trillion problem based on conservative estimates. About 2 to 5% of world's entire gross domestic product is attributed to be part of money laundering. So we are looking forward to an exciting session on how to detect money laundering in real time on the next session, looking at hops, as many hops as 11, 12 hops. So it's going to be an exciting session, guys. Please do sign up for it. We will cover flavors of money laundering, and we'll cover G-SQL queries just like we do in all our episodes.
Great. Thanks, everyone, for joining us today. We will be sending everyone who registered a copy of the slides and links to all of the things in the presentation and a recording so that you can review that as well. And there's additional links here on the screen, which we'll also send you via email. So I think we're going to end it now. Thank you, everyone, for joining us, and we hope you have a great day.